Hello, my people. I hope we're doing well. This is the second video for our test review unit. This is our second cumulative question for applications of integration. Let's go ahead and get started. Given the functions below, answer the following questions. Now you're given two exponential functions. F of x is equal to 2 to the x, and g of x is negative 2 to the negative x plus 4. Now, if you go ahead and you plug those into your calculator, you will get this graph. Okay? Basically, and if you want to sort of zoom out, press zoom 6, and you can see here comes 2 to the x, which is, I guess, sort of a parent function for the exponentials. And the negative 2 to the negative x plus 4 represents three different transformations on the original. It's a y-axis reflection, x-axis reflection, and moving up 4. And so they have basically the same shape, just the red one's been moved around and flipped around a little bit. Okay, I have printed out basically a zoomed in version of that. Okay, and basically what we want to do first, since we're going to be asked in part A to find the area between the curves, is we need to find those points of intersection. Now we're going to need a little help from our calculator. Okay. You could, if you wanted to find the points of intersection, you could take 2 to the x and set it equal to negative 2 to the negative x plus 4. Okay, and you could work that out largely algebraically. You probably are not going to want to. But seeing as, you know, it's always a good idea to review past knowledge, let's go ahead and do this. Just take a minute, okay? I need to basically solve this, and the first thing I need to solve it is I need to get rid of that negative exponent right there. So let's bring the 4 over, and let's turn this into negative 1 over 2 to the x. Let's go ahead and multiply through by 2 to the x, and that's going to, I'm not going to turn this into 2 to the 2x. I'm going to leave it like this, and you'll see why in just a minute. Now remember that things can have a quadratic structure without being formally quadratic. And this is exactly what's happening. This is something squared minus 4 times that something. And I can actually complete the square. Plus 4 plus 4. Now that seems a little kind of odd to us at times because we're just not used to seeing, I usually refer to these as quasi-quadratic. I have no better term for it, equations of quadratic form, whatever. And then of course I need to go ahead and take the square root of both sides, and that's plus or minus root 3. I get 2 to the x is equal to 2 plus or minus root 3, and I need to basically take log base 2 of both sides in order to get that x out of the exponent. Okay. Now, both of these will have a value because 2 plus root 3 and 2 minus root 3 are both positive numbers. And come to find out, they're actually approximately 1.900. Because they're 1.899999, something like that. Okay, see. And so I did log base 2 of 2 plus root 3 and log base 2 of 2 minus root 3, and I got 1.899968627, whatever. And then 2 minus root 3 was the negative of that. Now notice that I've stored those into A and B into my calculator because I want to use the exact values when I use them as limits of integration. Okay, so now that we have done that, we have basically figured out our limits of integration. Let's go back and let's actually do part A. We're going to find the area between the curves. Now remember that from the graph we notice that this right here is the transformed one, okay? It is g of x. This is g of x. This right here is f of x. And notice that g is on top. So we need our integrand to be g minus f. Okay? So g minus f. Now the area between the curves is going to go from A to B, and that's A to B according to how I've defined them in my calculator. And then I'm going to have g, which is negative 2 to the negative x plus 4, minus f, which is 2 to the x, dx. And so I can go ahead and bring my calculator over, and I'm going to do the integration here. I'm going to integrate, so 4, and I'm going to go from A to B, and because I've stored those values in, it's going to go to those. Now remember that I got to go back and maybe remember how I put them in. F of x is in y1, g of x is in y2. Okay, so I basically am going to need y2 minus y1 dx. And it is 5.204 approximately units squared. Okay. Now, show some value h for which the area found in part A is divided in half. Show your analysis. Okay. Well, let's figure that out. Now, I'm going to actually need to integrate on this. Let's go ahead and let's just set this up for now. Okay. Now, if I have 5.204, I know that half of that is basically just that divided by 2. But my variable, the thing that I'm looking for, is not kind of what's in here, but I need my variable to be kind of one of my limits of integration. So basically, I want a to some value of h for that same integrand, okay, and I need it to be equal to that, I need it to be equal to half of this, okay? So I need it to be equal to half of a to b of negative 2 to the x plus 4 minus 2 to the x dx. And of course, if I'm going to actually use the value, I can't use the approximate value. I'm going to need to go ahead and I'm going to store this in, and let's just, I don't know, let's call it C. I don't really know. Okay, so let's just store that into C, and we'll give ourselves a little notation that that's what we've done. So basically, this needs to be half of C. Well, if I know that, I can actually, and we haven't really talked about this, but since we're here, I can actually remember that there is the ability to define a function as an integral, okay? And let's go ahead and go to x, and then we'll have y2 minus y1 dx. Now, I want to know where that is equal to half of c, right? So I could just subtract, c divided by 2 so that I can just look for the 0, right? Okay. Well, let's go ahead and graph this. It takes a little while because you're defining a function as an integral, and it has to run each value through the integral, and so it winds up taking just a little while. I'm wondering how long this is going to take. Now, here's the thing. You could actually, because this is integrable by hand, okay? You could actually integrate that thing by hand and then set it equal to that half of c, right? Yeah, you're going to want to use your calculator probably. But the great thing about the integral sign, is you can actually put it in the y equals section, and you can actually use the stored values in there as well. Now this is obviously taking forever. Since we haven't really done any of that, I'll go ahead and skip on to that. But basically, this is the idea. You want to basically go from the beginning of your interval to some value for that same integrand, and you want to set it equal to half of that area, and then solve. Whether you need to solve by calculator or whether you need to solve by hand, whatever. Okay. Now, part C. Find the average slope for g on the interval 0 to 4. Is there some value of c in the interval for which the instantaneous rate of change is equal to the average rate of change? If so, how do you know? If so, find all such values. Now, remember, this is the mean value theorem for derivatives, and we need to basically determine whether the function, first of all, is continuous on the entire interval, and it is. Exponentials are continuous on their entire domain, which is negative infinity to infinity. They're also differentiable on their entire domain from negative infinity to infinity. And so g satisfies, just by the very nature of it being an exponential function, g satisfies both of the conditions for us to be assured that there are some values. Now remember that the mean value theorem says that the average rate of change will be equal to some instantaneous rate of change within the interval. So let's find the average rate of change. Now remember, average rate of change over an interval is just basically the slope between the two ordered pairs. So basically on 0 to 4, I need to figure out that, and then I need to set it equal to g prime of c. Okay, well, g of 4 is going to be negative 2 to the negative 4 plus 4 minus negative 2 to the 0 plus 4, all of that over 4. Okay, so let's go ahead and continue. Now, 2 to the negative 4 is 1/16. So you basically have negative 1/16 plus 1, right? Because 2 to the 0 is 1. So if you distribute here, those cancel out. And then you're left with 15/16 over 4, or 15/64. There's your average rate of change. Now, I need to find g prime of x, and I know that when I differentiate this, the 4 is going to go bye-bye. So really, I'm only worried about the negative 2 to the negative x. Now remember that that is basically that, right? Let's not get confused that the negative 2 is part of the base. But now I know that the negative 1 comes along for the ride, okay? I know that the 2 to the negative x sticks around. I know that I also get a natural log 2 in there, and then I also need another negative 1 to deal with the chain rule from here. Now obviously those two cancel out, and I'm looking at natural log 2 over 2 to the x. Now that means that I need to set 15/16 equal to natural log 2 over 2 to the x, and then I need to solve. And that means I get 2 to the x is equal to 16 natural log 2 over 15, and then basically I need to take log base 2 of 16 natural log 2 over 15. And that should be a value between 0 and 4. Let's go ahead and see if it is. Let's go ahead and do the log. So log base 2. And let's go ahead and turn that into a fraction. 16 natural log 2, all of that over 15, and the answer is, okay, well, oh, because I called it 16 instead of 64. Duh. That's what happens when I start going too fast. Okay, let's try that one more time. Let's just sort of scoot back in here and turn that 16 into a 64. And I get approximately 1.564, which is definitely in the interval. Okay. Now, that's part C. Let's go ahead and move on to part D. Now, what we want to do is we want to find the average function value. So whereas we use the mean value theorem for derivatives on G, we're going to use the mean value theorem for integrals on F. First, we're going to find the average function value. And the average function value starts with the area under the curve. And then I simply have to divide by the width of that interval. Okay. Now, when we are dealing with derivatives of 2 to the x, it obviously is 2 to the x natural log 2. But if I'm going the other way, it's 2 to the x over natural log 2, right? So I have 2 to the x over natural log 2, and I want to evaluate it from 0 to 4. Well, I don't want that in there, so let's go ahead and pull the natural log 2 out, and we're just left with 2 to the x from 0 to 4. Well, 1 over 4 natural log 2. 2 to the 4th is going to be 16, and then 2 to the 0 is going to be 1. And this is going to be 15 over 4 natural log 2. Now, that, as an average value, okay, is going to be, let's go ahead and figure out what that is approximately. 15 over 4 natural log 2. And that is going to be 5.410, approximately, right? Now, what I need to do is I need to determine when is f equal to that. Okay, so I just set 2 to the c, which is, of course, f of c, 2 to the c equal to that 5.410. And of course, I would store this into some value in my calculator and use the actual value rather than the approximation. And in solving for c, I know that this is going to be log base 2 of that 5.410, or more to the point, log base 2 of 15 over 4 natural log 2. And therefore, all I really need to do is basically take log base 2 of my answer, and that is going to be 2.436. So at x is equal to 2.436, we're going to get a function value that is equal to the average function value over that interval. Now, let's go ahead and see if that actually is the case. We're going to go ahead and put in the average value here. Natural log 2. Okay. Let's go back to the graph. Actually, let's zoom in a little bit. Let's go -4 to 4, and actually, since the interval is 0 to 4, let's go ahead and do it that way. And let's go 0 to 16, and boom. Okay, so this is 2 to the x on the interval 0 to 4. And here comes my average value over the interval. And we can kind of see that there is just as much overage here as there is over here. And in order to see if this is indeed the correct point, let's go ahead and calculate the intersect. And there it is, 2.436. Now, if you can't see that, remember that anytime you do a calculation like this, it stores it into x into your calculator. So you can go back to the main screen and actually use x as a stored value to get what you need. Okay. Alrighty, now that was D. Let's move on to E. E is find the volume of revolution around the x-axis for the region bounded by both functions. Okay. Now, we already have our limits of integration because we used them when we did the area. What I want to do now is I want to basically spin this around the x-axis. And doing that, this is going to be a washer, and I need basically to define g of x as my big R. I need to define f of x as my small r. I need to remember to square them both and actually put the pi out in front. So remember that I have these already stored into my calculator. Okay. I know that my g of x is -2 to the negative x plus 4. That is my r, okay? But that's also, remember, that's y2 in my calculator. y1 is my f of x, and that's 2 to the x. This is my big R. This is my small r. Okay, so this is sort of like a little legend or key over here. Okay. What I want is, remember, I've already stored -1.89996686 or whatever into my calculator. I need to put the pi out in front. I need to go from A to B. And then I basically need this quantity squared. So I need 4 minus 2 to the negative x squared. And all I did was just turn this around to basically, instead of negative, plus, it's just, a difference. Minus small r squared dx. Now, there probably is a way to simplify. There's a way to simplify and do the integration by hand, but since these are such wildly bizarre irrationals in terms of the limits of integration, I'm going to need my calculator anyway. Okay. And so what I'm going to do is I'm going to just remind myself, okay, that this is y2 and that this is y1. And so let's go ahead and put our pi out in front times, and you don't have to put the times, I don't think. I just always do. It's just a force of habit. A to B of y2 squared minus y1 squared dx. And what I get is I get approximately 65.401 units cubed. Okay. I hope that was helpful, guys. As with all of the other videos that I post, please be sure to shoot me a message to let me know if you have any questions. Yeah, just be on the lookout for the next video. Bye, guys.